Hey YouTube, my name is Raj and today I'm going to be showing you how to build a 5G connected air quality monitoring system using the S2 module and Superstack. This project is easy to build, easy to scale, production ready, and all the parts are available off the shelf. Let's jump right in. So this is everything we're going to need today. We've got a nice clear mounting box that we're going to mount everything in. We've got the sensors themselves. These are from SparkFun and Adafruit. The air quality sensor is an ENS160, and here we have a temperature and humidity sensor, which is the SHT45. We're going to use a temperature and humidity sensor to provide calibration information to the air quality sensor. We've got a relay board, little relay module, so this could be used to turn a fan on and off, and we'll automate this as well in our code. We've got the S2 module itself, so this will be the heart of the system. We've got some cables to connect everything. The interface that we use here is called Quick or Stemma QT. This is the same interface SparkFun and Adafruit and a lot of other vendors, these kind of sensor module vendors use these days to connect sensors together. And then we've just got some mounting hardware. So these are just some nylon screws and standoffs, and these are the case screws that arrived with the case. On the tool side of things, we just have a little hand drill, seems charged, some drill bits, a marker pen to decide where the holes go, and some screwdrivers and some bits for the screwdrivers. So I'm going to start by just roughly placing all the different boards inside the mounting box. And once we're happy with the placement, I'm going to use the marker pen to make some dots, and then we can drill some holes to mount everything. So I think a good place for the S2 module would be on the left here. There's this sort of annoying lump in the middle of this mounting box that's going to make things a bit awkward to place right in the middle. The relay board I think can go right on this end, and the two sensors should be perfect right in the middle here. Something like that. That probably works. And then let's mark a few holes. See if I can do this without stuff sliding around. Perfect. So I have all the holes marked out now, and now I'm just going to drill them out. I'm going to start with this really small drill bit. This is a 1.5mm bit, just to make sure that I get these little dots in exactly the right place, and then we'll go in with the proper size for the mounting hardware. The pilot holes are now drilled. And of course, because this is an air quality monitoring system, we're going to need some airflow through this box. So I'm going to measure out a few holes along the sides, this side, the long sides as well, and just drill a few holes. And of course, later on, we'll need to drill a hole for the USB power connector and also the wires that would go into the relay. And there we go, all the pilot holes for now are drilled. The mounting hardware is M2.5, so I've got a 2.5mm drill bit here. So I'm going to make all these little pilot holes on the bottom bigger, up to 2.5mm. So now, just so these screws sit flush, I'm going to go in with a 6.5mm bit just to add a little bit of a countersink so these things can be flat on the base of this case. That should do. So I've also drilled out the holes for the airflow. So there's two on the top and bottom and one on each side. And now we can start mounting all the boards. So first I want to mount the S2 and the relay board, and we can then mark out the final 2 sets of holes to drill, which will be for the power connector and the contacts for the relay. So here I'm just using the little standoff to space out these boards, so they sit a little bit higher from the bottom. So now I'm just going to mark out the placement of the USB connector and these holes. I'm just going to eyeball them with a marker, and we'll take the boards out again, drill the last couple of holes, and then we'll mount everything down. So I've just roughly marked out where these holes are going to go. They don't have to be super perfect because they're going to be quite big holes for the wires to get in, so you won't really notice if it's off ever so slightly. So now all the holes are drilled. You can see this one for the USB connector got a bit close to the airflow hole, but we just about got away with it. Should be all right. So now it's time to finally mount everything. Let's screw it all down, connect everything together, and we're ready to close it up. All right, everything's mounted. Now let's wire everything up. You can use any of these ports really, of these 4 to connect these sensors. You can also daisy chain them. One option could be to daisy chain from here to here, but that'd get a bit too close to this board. So I think I'll go from this one to here. This cable's a bit long, so let me get a shorter one. The nice things with these cables is that they're available in a pack of different sizes. You also get ones which are, for example, like this to these female headers, so you can connect them to a board that doesn't necessarily have the quick interface. There we go, everything's wired up. For the relay, I've already soldered on some pin headers here to help us connect these. This is the only soldering I've done because this module didn't come with any pins soldered to it. It came with the pins, however. The red and the black are VCC and ground respectively, and the blue and the yellow are 2 signals coming off this port, and this is port A as labeled on the S2 module. So I've connected the pin A0 to the signal, and pin A1 is just on a disconnected pin. So I've just soldered a pin. It doesn't actually go anywhere on this board. It's just to stop the extra header flapping around. The other thing you'll notice is that I'm not putting the wire back here. Generally, you should avoid putting anything too close to this antenna. So I'm just going to leave it like this for now. You could actually tuck it in underneath the board, but just to keep everything nice and clear, so when you're looking at this you can see what's going on inside, I'm just going to leave it here for now. So here I am in Superstack. Superstack is a control center for all of your devices. From here you can see what devices are online, you can edit the code, see the logs and get the data. Everything is managed from this one platform. If you haven't already, go ahead and sign in. Let me do that right now. And then click on the current deployment. And if you want to create a new one, you can, but here I've already got one, so I'm going to select that one. Then we can go over to the Devices tab and click Add Device. Now first you want to make sure your S2 module is powered on and that it's connected to the internet. You'll know it's connected to the internet when the net LED becomes solid. Then scroll down and we can enter the IMEI of the S2 module. This is written on a label on the back of the module. We can also give it a name. And then click Add Device. Next, you want to click the button on the S2 module. That is a pair button. And as soon as you click, you'll see it appear in the device list. So now we can finally screw down the lid on this box, mount it somewhere, and everything else will be done from Superstack. So I've moved over to the code tab here. And before we start, we want to select the correct device. In case you have multiple devices in your deployment, you'll need to come over here and make sure you select the right one. So here I'll select air quality sensors. And there's a couple things we want to open up before we get started. And that is the datasheets for each of the sensors. And we also want to open up the Lua API reference over here. Over here, we'll be able to find reference for how to write our Lua code later on. So let me jump back over to the code tab here. And I'll start by deleting these comments. And before we start, there's one important thing that you might need to check regarding your sensors. By default, the S2 module provides 1.8 volts to each port, but your sensors might require a higher voltage. And you'll be able to find this by looking at the data sheets. So in this case, we can see that 1.8 volts is actually just fine for both of these sensors. But in case your device requires a higher voltage, the way you can set that is with the following code. So if we go over to the Lua documentation here and select this power section, and if we scroll down, you'll find this API for device.power.setVout. So if you pasted that in and typed in 3.3 volts, as soon as I save this, the voltage on all of the ports would change to 3.3 volts. In our case, we don't need that, but if your sensors require that higher voltage, just keep that in mind. So let's try to scan for our devices. We have a handy API for scanning the I2C ports. And you can find that over here. So if I just scroll to the index at the top, under I2C communication, there is an API for doing an I2C scan. So let's copy this. So if we just leave the argument here blank, it'll by default scan on port A. But we know that we've connected each device on port E and port F. So let's provide those as arguments here. So if I type port equals port A, port E, and then I'll copy this and I'll type port F over here. And let's add a print so we know what port it's scanning on. Port E, and print port F. Okay, so if I save this, the S2 module will update over the air and print out the devices it finds on each port. So here we can see that on port E we didn't find anything, but port F found a device 0x53. And on port F is the air quality sensor, and on port E should be the temperature sensor. And I'll come back to why this didn't show up later on, but this is an interesting quirk regarding this particular temperature sensor. The way the scanning function works is that it goes across every address, I2C address on that port, and it tries to prod for device. And this works on most I2C devices, but this particular temperature sensor doesn't work in that way. But we did find the air quality sensor, so we'll get started with that, and I'll show you a little bit about this temperature sensor quirk in a little bit. So now we could get started by reading both of these data sheets and learning how to configure and read each of the sensors. But that can be quite tedious, and if you just want to get started quickly, what I like to do is throw the data sheets into ChatGPT and get it to give you recommendations on where to start looking through the documents. So over here on ChatGPT, I've uploaded the air quality sensor datasheet, and I've asked it to help me figure out how to read the air quality index, CO2 and VOC levels from this sensor over I2C. Here I've also pasted in the Lua API for the I2C commands that we have. And if we scroll down, we can see that it's already starting to give us some recommendations. So we've already spotted the device address as 0x53, so this seems correct. And here it's given us a list of the basic registers we need to interact with to set up and then start reading the data.
So what we want the air quality sensor to do is report back a few of these air quality metrics periodically to Superstack, such that we can read those values and maybe show it on a dashboard or use the agent feature to actually do something with that data. So this is a basic template of how we're going to build the code up. So over here you see the address that we captured earlier on. And in a loop, we need to get the air quality values, and then we're using network.send data to send each of these values to Superstack, and then we just sleep for 3 seconds. The first thing we need to do is configure the operating mode of the air quality sensor, and that is done using this op mode register 0x10, and we need to set it to standard, which is the gas sensing mode. So over here I'm writing 2 bytes over I2C to the device, and the first byte will be the register and the second byte will be the value to set in that register. Again, remember that we need to send this out on the correct port, and the air quality sensor is connected on port F. So all operations going to the air quality sensor will be on port F, and all operations going to the temperature sensor and humidity sensor will be on port E. This is just the Lua string. It's just a couple bytes in a row. If you're used to programming languages like C, you might know that you can't put a 0 byte inside a string, but Lua doesn't have that limitation. So if I did 0x0002, this would send the byte 0 and the byte 2 out over I2C. This in Lua is completely allowed, and so you don't need to worry about these kinds of details over here. Another way of doing it is, as ChatGPT over here suggested, is using string.car, and here you can just provide a series of numerical hex values. It's the same thing. Before we can actually read the air quality values from the sensor, we need to provide the sensor with a temperature and humidity calibration. And to get those values, we'll need to talk to our other sensor, which is the temperature and humidity sensor. If we look at the data sheet, we can see there is the command fd, which is used to actually measure the temperature and humidity. And remember that little quirk I mentioned before. So essentially what we need to do is put a little pause in between the writing of the register we want to talk to and the reading of it, because in that time the sensor is doing the conversion. The whole sensor works like this for all of the commands, and that's why it didn't respond on the scan earlier on. So over here I'm writing 0xfd, and again on port E, and then I'm reading out 6 bytes from the same device. We need to add the address of the device. And because we didn't find that before, we should look up the address on the datasheet or use ChatGPT to help us do it. And that address is 0x44. So now I'm reading those 6 bytes over into response here. This should actually say local response because it's a new variable. And if I save this, periodically, every 3 seconds, the temperature sensor is now being read from. The values in response we now need to convert into the temperature and humidity values. So within these 6 bytes is the actual data. Now this may seem a little complicated, but over here in the data sheet, it shows you exactly what data it's sending back. So the first 2 bytes will be the temperature data, and then there's a CRC of the temperature data, and then there's 2 bytes of the humidity data, again followed by a CRC. So ignoring the CRC, essentially we need to read byte number 1 and 2, and then number 4 and 5. Once we read those bytes, we need to attach them together. Here it's 2 8-bit values, i.e. 2 bytes, and we need to turn them into a 16-bit value because both the numbers are actually 16-bit. I've got the code over here already. These 2 lines are taking, so for temperature, we're taking byte 1 and byte 2. Remember that Lua is 1 indexed as a programming language. So if you want to access the first element of a string or whatever it is, you would do 1 instead of 0. And humidity is on bytes 4 and 5. So here what I'm doing is taking the first byte, shifting it to the left by 8 bits, and then ORing it with the second byte. And this turns our unsigned 2 8-bit values into an integer 16 value. Same for humidity. So the calculation of how to turn these 16-bit values into temperature and humidity are shown over here. And I've just turned this into code, to Lua code over here. So now let's paste in the calibration code. And again, this might look a little bit scary at first, but it's not too bad. So first, we need to convert the temperature and humidity into a value the air quality sensor expects. And again, these two calculations are just found in the datasheet over here, and ChatGPT can also recommend this to you. And we simply write both those values over to the correct registers on the sensor. So over here, we're writing to this register 0x13, which is the temperature calibration register. And it takes 2 bytes, the high byte and low byte of the temperature value. And these 2 lines are just formatting it correctly. So it sends out this number as 2 separate bytes. Same thing for the humidity. And again, that can just be found down here. All of these are shown as examples in the datasheet, and ChatGPT can help you figure this out as well. Now we're finally ready to start reading out the actual air quality values. So I'll paste in the code over here. So what this is doing is we're first writing the register value, and then we're reading something from it. Here we're reading 3 registers, the 0x21 register, 0x22 register, and 0x24 register. Again, ChatGPT told us which registers exactly to read. And if we look at the data sheets, we can actually see these 3 registers that give us these values. So this register gives us a number from 1 to 5, which represents the air quality. And this is just the lower 3 bits of the register. So all we're doing over here is taking the value that we get back, the 1 byte that we read, and we're just ANDing it with 0x07, which represents the 3 lower bits of a byte. For the volatile compounds and CO2, just like we did for the temperature sensor, we're sticking together the first byte and the second byte, and the second byte is shifted over by 8 bits. So now we can delete all of these things because we're reading the real values. And if we save this, give it a moment to update, we should see that the reading starts again. And now we hop over to our data tab, we can start seeing that our values, which were 0 before, now have real values. So the air quality index is 1, carbon dioxide is 434. I believe this is parts per million. Humidity is at 47%, and volatile compounds is 39. I think the units for this is parts per billion. So now if I blow on the sensor, we should see these values go up. Now let me scroll down. And there we go. We can see the carbon dioxide level has gone up, as has the humidity. Now there's one final thing we can add, and you remember the relay we added. So this relay could be used to turn a fan on and off, for example, when the CO2 level is too high. And so let's paste that code in over here. And what this code is doing, if the CO2 level goes above 800 or the volatile compounds levels goes over 2200, then we set the relay, we turn it on. And remember the relay pin is attached on A0. Otherwise we turn it off. And that is just done using this digital set output function. So as soon as I hit save, we're all done with the code that we need to write. And you can see within less than 70 lines of code, we're reading back 4 air quality metrics, reporting them back to the cloud, and even setting a relay on and off that could control a fan. And all of this without any debuggers, without having to have the device in close physical proximity to your lab. All of this can be done remotely if you wanted and debugged remotely. And it's all real time. As soon as you make changes and save, you can see the results instantly. Now that your device is set up, you might want to start reading that data out to a dashboard or sending the data downstream so it can be used with other applications. And Superstack easily lets you pull out the data using REST APIs. If we go over to the Superstack documentation and scroll down to Data API, we see an example of how to use the curl command to read out some data. And you can easily do the same in JavaScript, Python, or many other languages. So let's start by copying this, and we can jump into a terminal, and we don't need the time arguments over here or the groups, and so we can delete those. And then we only want to filter for the air quality sensors. So here I will jump back to Superstack, click on devices, and then select the device name for air quality sensors and paste that in. We want to replace the deployment ID with our deployment ID. And you can see that by going into the settings tab. Paste that in over here. And then we want to enter our API key. The API key can be generated also on the settings tab. If you scroll down to where it says API keys, you can click create new key and it'll generate one for you, and then you can copy it from here. Paste that in. And there we can see it's returned back all of the most recent data for the air quality sensors. If you want to limit this for just the last few readings, you can keep the time argument in there and just give it the last hour, for example. If you visit demos.siliconwitchery.com, you can see a simple dashboard demo that we've built that uses that same REST API and periodically pulls that data out and shows it as some nice graphs. If you want to build your own dashboard, we have this as a GitHub repository you can take a look at. So this just consists of an index.html, so one HTML file, and a couple JavaScript files. Everything really happens over here in main.js. Finally, let's take a look at the AI features of Superstack. Here on the Agent tab, I can ask questions about my deployment and my data and get real-world insights on that data. If we jump over to the Devices tab and click on Air Quality Sensors, you can see I've already pre-filled this device role. Here I've specified what kind of sensors are connected to the device, as well as things like the units. Giving this kind of context is really good for the AI because it helps you understand the data a little bit better. So we can close that, go back over to Agent, and while you can set individual device roles, here you can set an overall deployment role. Let's ask it a question. And here we can see that the agent thinks that all the levels are nice and safe. If we click on reasoning, we can see how it actually determined those answers. So there we have it. That was the air quality sensing demo using the S2 module and Superstack. We hope you enjoyed this video. If you did, be sure to like and share with your friends if you think they'll be interested in this kind of content. We'll be making more demos just like this one, so be sure to check out our upcoming videos and check out our blog as well. We have some tutorials and other helpful guides there on how to use the S2 module and Superstack platform. Hope to see you in the next video. Catch you later.